Okay. Let's start with, I'll just start with some basic info. You know when it is. It's on Thursday, February, I was about to say May for some reason, February 25th, which is this week, this Thursday. It'll be available again from 11:59 p.m. Until on the 24th until 11:59 p.m. on the 25th. So 24 hours. You can choose whenever within that period you'd like to do it. I do not recommend waiting until the last possible hour because that just is stress that you don't need. So start it early and make sure you have time and space to do it. It is covering chapters 1 through 5, which is also coincidentally weeks 1 through 5, and there's no R on it. Somebody asked about that. R is technically chapter 6, but thank you for asking, whoever asked that originally. That's a valid question, and there is no R on this midterm. That's what I wanted to say about that. In terms of the format, there are 2 parts. Part 1 is sort of similar to the quizzes, so 15 multiple choice or short answer Mobius questions. And then there are 2 marks each, 2 points each for a total of 30. And part 2 is 3 full solution questions, which are 10 points each. And one of them has a 2-point bonus question. So you can theoretically get up to 62 marks out of 60 if you ace everything. So if you get one of the part 1 questions wrong and you want to redeem yourself by doing those that bonus question, then it's still possible. So that's the basic structure. And so the Mobius questions will be delivered the exact same way that you're used to seeing the quizzes so far. Although you only have 1 attempt, and we're not going to tell you whether you're right or wrong after each question, obviously, because everyone's getting slightly different questions, but it's open for so long. So you'll be able to go through in order, answer the question, and then move on, and you have a good amount of time to do that, and you know how many questions there will be. They're all equally weighted, so you can pace yourself and make sure that you're on track. The timing, I mentioned this as well. We've got 90 minutes for each part. And that is twice what we think you'll need. We think it would probably take 45 minutes for someone who's well prepared to get through these questions, but just in case people's internet is a little bit slow or whatever, or you need to look something up, then we're giving you 90 minutes for each part. And you can do those parts back to back if you want, or you can do them separately. You can have a break in the middle, study some more in the middle, and you can do them in either order. You can do the short answer questions first and then the full solution, or the other way around, whichever way you like. They're both worth the same amount. They're both worth 30 points. So there's no particular strategy I would recommend, but whichever one you feel like you want to do first, do that, and then you can either take a break or you go straight into the second part, whatever you like. For the part 2 in particular, you have to also upload your solutions to Crowdmark. As well, with a screen cap of the question, because some of the parts on those questions are going to be things that require you to say graph something or draw something or answer in a sentence or prove something or something like that, questions that are not just numerical. So you will put your numerical answers into Mobius and then upload your full solution to Crowdmark. And we're giving you an extra half hour to do that on top of the 90 minutes. So I'm going to add here like plus 30 extra minutes to upload to Crowdmark. Sorry, squishing at the end there. So people have been asking about that. The 2 parts are separate. The part 1 obviously you just do it through Mobius. Part 2, your questions will be given to you through Mobius. You take a screen cap of those and then answer them either on paper or electronically, like with an Apple Pencil or whatever, any stylus, or typing even, whatever, LaTeX if you're super fancy, whatever you like, and then upload that to CrowdMark. And you get an extra half hour to do that uploading part, just because we don't want to take away from the 90 minutes. I saw a question right away, how should we graph something? So for, like, if you look at the sample part 2, there was a request to graph a CDF of a random variable, and so you can see how to do that. There's also examples in the videos, I believe, and certainly in some of the course notes, of what graphs of CDFs of discrete random variables look like, right? They look like right continuous step functions. You could also graph a PF, a probability function, using a histogram, or drawing a Venn diagram we wouldn't require you to draw a Venn diagram, but really, really often a Venn diagram is a very handy way to solve a problem. So that can be part of a solution. It's hard to put a Venn diagram into Mobius, but it's easy to put it into CrowdMark. So for the CrowdMark, that's what we'll be focusing on marking, because it'll have both your process and your final answers in it. All right. In terms of materials that you're allowed to use, you can use anything on the course website or Piazza, basically. Anything on Learn or Piazza is fair game. So if you get a question and you're like, oof, I know exactly where in a video that it explains something like this, you can go and watch that video. Go for it. You do remember you have 90 minutes for each part, so you can't watch a video for every question, but if you want to go look something up in course notes, in an example that's been posted, in a discussion that happened on Piazza, maybe a thought question, you're absolutely allowed to do that, but please do not go outside of those parameters. So we've given you a fairly generous amount of material that you're allowed to access, and please don't look outside of that. So don't Google things, don't talk to other folks, just focus on your own knowledge and what you can look up from the resources that we've provided. I think that was everything I wanted to say about the midterm. Oh, just we will be asking you to upload just your signature. Like, you don't have to print anything out, just a signature, indicating that you agree with the academic integrity, so that you haven't shared the questions with anyone and that you haven't accessed anything outside of these materials. And that'll be part of the CrowdMark. Question 0 on CrowdMark, I guess, will just be for you to upload your signature. And an electronic or a physical, where you take a picture of it, both of those would be fine. I see a question again. For the Mobius portion, we get 15 questions and 3 extra ones for the CrowdMark portion. Essentially, it'll be 2 different links. There'll be one link for the part 1, 90 minutes to do those 15 questions, and you can only go forwards. And then whenever you're done that, great. And then part 2 will be another link to Mobius as well, to provide you with 3 full solution questions, and each of those questions is unique to you. So every single person has a unique question for all of the part 3 and all of the part 2 and many of the part 1 questions. And so yes, the second part, you have another 90 minutes. We think it'll only need 45, but we've given you 90 to do those 3 full solution questions, write them up, and then an extra half hour to upload the scans of your solutions to CrowdMark. Okay, any other questions on the basic info, format, coverage, etc. of the midterm? I will check Piazza and I will check Learn. Not Learn, sorry. Check Piazza and I'll check the chat here on Twitch. Nothing on Piazza and nothing here on the chat other than that. Okay, great. So that's the basic format. And again, you can do those parts in either order, and you can take a break in between if you want or not, and just make sure that you're using the resources we provided for you and nothing outside of that. So next thing I want to move into is sort of general questions. So I'm going to scroll up with this. And the first one I saw was Course Notes 3.6, question 3C. Okay, I think I know exactly what the issue is. And the question I think you have is, why is 3C done differently than 2C? Because they seem similar, but they're solved in different ways. Is that kind of what you were asking about, that person? I think I can read your mind. Yep, okay. So what I'm going to do is actually do both of them. I'll do 3C and I'll do 2C, but I'll start with 3C and then I'll do 2C afterwards and then point out why they're different. So for 3C, we have 5 tourists planning to attend Oktoberfest, and each of them selects one of 7 different locations. So I'll just write the key details. 5 tourists, each chooses one of 7 locations. And the question then is, for part C, what is the probability that 2 tourists attend one location and 3 tourists attend another location, as in like a group of 2 and a group of 3? So C is the probability to attend one location, the other 3 at another location. Just like that. So for this, we want to think about 2 things. We have to figure out what are the groups of taking these 5 tourists and splitting them up into a group of 2 and a group of 3. And then once we have those 2 groups, which locations are they going to attend? So to split up these 5 people into a group of 2 and a group of 3, we could say, well, let's choose 2 of the people, and then we have a group of 2, and then the other 3 people automatically form the group of 3. So this is the number of ways to form the groups. And then what we're going to do for each possible split of group of 2 and a group of 3, we need to assign 2 locations. But they have to be different. So there's basically 7 choices for the first group to go to, for the pair to go to, and then only 6 choices for the group of 3 to go to, because they can't go to the same as the group of 2. So the way we could write that is 7 to 2 factors, basically. And that's the way of choosing locations. And then, so that's all the total number of ways to split these 5 people into a group of 2 and a group of 3, and then assign a location to the pair and a different location to the triple. And that, of course, is our numerator, and then we want to divide by the total number of ways that these 5 people can choose from the 7 different locations. Well, when people are choosing locations, 2 people can absolutely choose the same location. So if we think about those questions, are we allowed to repeat objects? Yes, because tourists can pick the same location. So we have 7 to the power of 5 for the bottom, which is the total number of ways that these 5 people can each pick one of 7 locations. So that bottom is total choices or whatever. So that gives us the probability for part C here. I don't care what the numerical value is. You could calculate that if you like. But we basically have taken 5 choose 2 to split our group up into a pair and a triple, and then assign a location to each of those, and then divided by the total number of ways that these people can make these choices. But compare this to question 2, part C. So I'm going to scroll this down just for a second. So same section, but question 2, part C, is where we have 6 stops on a subway and 4 passengers. So it's basically the same kind of setup. We have 4 passengers and 6 stops. Same kind of setup. But here, part C is asking that 2 passengers get off at one stop and the other 2 passengers get off at another stop. So similar again, we want the probability 2 at one stop and the other 2 at another stop. So at first glance, at first and second glance, these questions look very similar. So I scroll down here. We have 2 attending one location, 3 attending another. Here we have 2 attending one stop and the other 2 at another. So let's do the same thing. What we're going to do is say, let's take our 4 people and split them up into a group of 2 and another group of 2. 4 choose 2. And then we want to pick 2 stops for these 2 groups to get off at. But here, we actually don't care about the order in which we assign stops to groups. And we don't because the two groups are the same size. That's the difference here. So we have 6, choose 2. Sorry, this is for the groups. This is for the stops. And then the same thing on the bottom, we'd have 6 to the 4 for the total choices. So the big question, I'm going to use a different color of ink because it's so important. Why is this different? Why is it here with replacement and here with replacement and here without replacement? The reason is, again, because the two groups of 2, once you split them into 2 groups, you'll double count if you assign the stops to the groups in order. Another way of thinking about it is the number of ways to take a group of 5 and split it into a group of 2 and a group of 3 is 5 choose 2 ways to do that, right? You write them out. There's 10 ways to do that. But the number of ways to split a group of 4 people without assigning stops to them, just to split them into a group of 2 and another group of 2, is only 3, not 4 choose 2, which is 6. So the groups being the same size means that if you tried to do it the way we did question 3, part C, you would double count everything exactly twice. Because you would basically say, like this would say, let's say you split the groups into A and B and C and D, and then you're going to take A and B and assign them to stop 1, and C and D and assign them to stop 2. Okay, that's one possibility. But this way, if we did it without replacement, sorry, if we did it with order mattering, that would be the same event as choosing C and D to be your first group and A and B to be your second group, and then assigning your first group to stop 2 and your second group to stop 1. If we did it with a 6 to 2 factors, if that was used, that would double count. That would count those 2 exact same events as being 2 different things, when really they are the same. So if we use 6 to 2 factors rather than 6 choose 2, we would double count every outcome. So if you want, you could think about 6 to 2 factors and then divide by 2 because we're getting rid of the double counting. But that's the same thing, right? 6 to 2 factors divided by 2 is 6 choose 2. Again, the other way we think about doing it is if we want to, instead of taking the groups and making a first group and a second group, we could just say, how many ways are there to divide 4 people into 2 groups without giving them labels? And there are 3 ways to do that. If we have A, B, C, D, we could do A with B, and then by necessity C with D. We could do A with C, and then B and D are together. Or we could do B and C, and then A and D are together. Those are the only 3 ways to divide 4 people into 2 groups if we're not assigning labels to those groups. So it could be, instead of the 4 choose 2, it could be 3 ways to do that, and then 6 to 2 factors for assigning stops to those 2 groups. So either way, it ends up being the same thing. We're taking 4 choose 2, which is 6, times 6 choose 2, which is 15, I think. And then divided by 6 to the 4. So hopefully that helps a little bit. That's a really, really common source of confusion, the similarity and yet somehow difference between those 2 parts, 2C and 3C in chapter 3. Does that help? Awesome. Can you go over some examples where we would use the Poisson distribution? Absolutely, yes. So go back to normal color. Poisson. Or the Poisson process or the Poisson distribution. I guess both. I'll do both. So there's tons of situations in the world that could be relatively well modeled with the Poisson process. And the key is thinking about something that can occur at any time, so it's not like divided up into discrete trials like flipping a coin or rolling a die or something like that, but something where events can happen at any time. So like lightning strikes during a storm, or visits to a website, or there's a great little MathSoc comic that I posted that they sent me where someone's counting hits on their video or views on their video. So things that can occur kind of one at a time, where there's no theoretical maximum number of events that can occur in a period of time, and we assume that they're occurring at some kind of constant rate. So I'm going to just jot down some of those ideas. So we have events occur one at a time. Independently. And at a constant rate. Now, in reality, of course, many of those assumptions, oh, sorry, I'm scrolling, there we go, my face is always in the way. Many of those assumptions would not hold. And it's really good, in fact, we often ask you to, on past midterm questions you might see, ask you to think about whether those assumptions would actually hold in reality. So imagine you're talking about, again, lightning strikes during a storm. Maybe they are independent, maybe not. Maybe one will cause another one. Maybe they occur at a constant rate, maybe not. Maybe there's sort of like periods of higher activity and periods of low activity. If we're thinking about traffic accidents, they might not occur independently either. If one car bumps into another car, that could cause another one to hit that. Or if the constant rate might not be there as well. There would probably be higher rates of accidents during busier times of traffic and not as many accidents during the night. So it's always good to think about whether those assumptions would hold in real life, and they often don't hold perfectly, but sometimes they hold reasonably well enough that it's still a useful model to use. So that's the idea with the Poisson process. And to get a Poisson random variable, that is doing a specific thing with a Poisson process. So if you watch a Poisson process for a specific amount of time, and this Poisson process has rate lambda for t amount of time. And let x equal the number of events that you observe. Then that's what we get our Poisson random variable. So x is a Poisson random variable with parameter mu equals lambda times t. So the longer you watch this process, the larger t would be and the larger the parameter would be of this random variable. And that makes sense. If you watch, a particular intersection for twice as long, you would expect on average twice as many cars to go through. And if the rate itself is higher, you would expect more events to happen. So that's the idea with the Poisson distribution in terms of how it comes from the Poisson process. We're sort of counting up the number of events that occur in a fixed known interval of time within a Poisson process with this constant rate lambda. But there is another way that the Poisson process can come up. So as well, a Poisson with rate with parameter mu can be an approximation, a binomial random variable with parameters n and p, where n is large and p is small. So n is going to infinity and p is going to 0, with the product n times p remaining constant and equal to mu. So this is a different way that the Poisson distribution comes up as sort of the limiting case. It's called the limiting distribution of the binomial. As we let the number of trials go to infinity, while the probability goes to 0 at the same rate, so that the product of those two parameters is constant, then we can see that the limit of the binomial probability function turns into the Poisson probability function. So again, I strongly recommend checking out the comic from MathSoc, which really illustrates that super well. About like, you could think about an hour as 60 trials, each of which is a minute long. But you could also think about that as 3,600 seconds, each of which has a very small probability, or like, even more microseconds or whatever, milliseconds, there we go. So you can take an amount of time and chop it up into intervals, and then think about the Poisson as being a limiting case of the binomial. So does that answer your question? I didn't go over any specific examples, but generally the keywords that you're looking for when you know to use a Poisson distribution is something that either literally says Poisson process or hints to you that the Poisson process is involved. So if you check out some of the questions in chapter 5 at the back, they say like, suppose events occur, uniformly throughout time with little chance of two or more happening at the same time. That's kind of code for it's a Poisson process. And then within that, if you are looking at counting up the number of events within a fixed amount of time, then you want to use your Poisson random variable. Okay, great. Yes, thanks. Okay, next question. Is it possible for you to give us more practice on set notations, such as calculating A and B and not A or B and such? Absolutely. I will make up a question for you. Okay, so let's go here. Set notation. So I think everyone's cool with the individual operators on their own. So union is A or B or both. Intersection is A and B, and complement is the opposite. The tricky stuff happens when you're sort of combining them together. So I'm going to just make up some questions here. You know what? I have some dice. I'm going to roll some dice and make up some stuff. So let's suppose you're rolling a 12-sided die. I have a D12 here. There's just more possibilities. And we'll let A equal the event, I don't know, that we get a 4 or an 8 or a 12. So something multipliable by 2, whatever. We'll let B be the event that we get, I rolled a 4 again. I'm just making stuff here. 11, okay, how about this? 10, 11, or 12. And if we need another event, I'll make one up. So what would be A union B? You can type it into the chat if you want. That would be 4, 8, 10, 11, 12. So we could find the probability, right, of both of them. Oh yeah, sorry, A intersect B, or just AB. That's going to be just 12. A complement, right, is anything that's not in A. B complement is anything that's not in B. So we could have, let's say, A intersect B complement. So that would be anything that is in A and not in B. So what would that be here? If we want it to be in A, we want it to not be in B, then we have just 4 and 8, right? So because those are in A and they're not in B. What are some other combinations we could do? Let's say B complement union A complement. Ooh, let's go with that. So B complement union A complement. We could do this directly. We could think, okay, all the things that are not in B, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, and all the things that are not in A, oh boy, 1, 2, 3, 5, 6, 7, 9, 10, 11, and the union of all of those. So that would be pretty annoying to do, but you could do it. You'd write them all out and you'd put the union, anything that's in either of those things, which is going to be a lot of them. Or you could use De Morgan's law, which is much faster. So B complement union A complement is the same as B intersect A all complement. So De Morgan's laws, remember, is sort of if you're taking, I always learn about it this way. So like A union B complement is A complement intersect B complement, and A intersect B all complement is A complement union B complement. So this is how I was taught it. If you break the line, you change the sign. Hey, so you're breaking the line, you're changing the sign. If you've never heard that before, you're welcome. Now you have. So we can write B complement union A complement as just B intersect A all complement, which is, we know that in A intersect B is just the number 12, and so this is going to be everything except 12. So 1, 2, 3, up to 11. And so we could find the probability of all of these things using the classical definition of probability. So the probability of A here is, I guess, 3 over 12. This is 3 over 12 as well. A intersect B, the probability is 1 over 12. And A union B then is 3 over 12 plus 3 over 12 minus that intersection, which is 5 over 12. So we could get this by 3 over 12 plus 3 over 12 minus the intersection 1 over 12, because we don't want to double count that intersection. And I don't know if that was kind of what you meant in terms of an example. If you wanted one sort of like a little more theoretical, I could do that too. But my very strong suggestion for dealing with any kind of set notation is to use a Venn diagram. So let me do like another not so specific example. So another example. Let's say P of A is, I don't know, 0.5, and P of B is, I don't know, 0.1. I'm making stuff up. And we don't know anything about whether or not they're independent. So what we can do is sort of draw a Venn diagram here. That's A, and that's B. I'm trying to do them roughly proportional. They're not, but I'm trying. And if we know, let's say, P of A intersect B, let's say that is 0.05, then we know everything else there is to know, right? So if this intersection here is 0.05 and B as in total is 0.1, that means this part here is also 0.05 and this part here is 0.45. And then because the entire sample space has to add up to 1, that tells us that the outside here, this where it's not A or not B, I guess like the outside, is going to be the 1 minus the rest. So 1 minus 0.45 minus 0.05 minus 0.05, which is 0.45 actually. Weird. Anyway, I pulled these numbers out of the air. But once you have this, you can do anything. Right? You can ask for what's the probability of A complement intersect B complement, or A complement intersect B, or whatever, like any combination. Once you have these 4 numbers, you can find them just using the diagram. So again, I strongly encourage using Venn diagrams to help sort of visualize if you find that helpful. You don't have to, and you could just use formulas, but it's often easier to visualize what's going on and what the various combinations of events are when you have a diagram like this to look at. So the person who asked that question, is that a satisfactory answer, or would you like some more? I'll give you a second to answer, and then I'll move on to the next question. Okay, I see another one. It says, I'm good, but need practice. Yeah, no worries. There's a few practice ones. I did post a part 1 practice. If you hadn't seen that yet, check that out. We will be putting up, if it's not up already, the all-star questions from the first collaborative assignment, and many of those have some great parts that you could try as well. And there's, again, lots in the course notes as well. So yeah, practice drawing Venn diagrams, super helpful. Okay, next question. I had a general question based on a question outside the course notes. Okay, no worries. Suppose we have to make an 8-character password with at least 1 uppercase, 1 lowercase, and 1 number. How do we calculate the number of passwords possible? Yikes. So that would be tricky because of all of those different conditions. It would be really easy, in fact, I think it is one of the questions in the course notes, to have one condition. Because you could basically say, let's take all possible passwords and then subtract the ones that don't have any uppercase letters. Done. That's how you would do it to satisfy one condition. But to satisfy multiple conditions, you sort of have to think about dividing it up into cases. So maybe I'll scroll up here and I'll sort of write this down. So this is not from anywhere in particular. But if you have a password where you say 8 characters, at least 1 uppercase, at least 1 lowercase, and at least 1 number. So what you would do, I think I would still do it by subtraction, because it's just way too many combinations to do it by sort of additively figuring out how many ways to construct passwords like this is. So we would start with the total number of passwords, which would be, if there's 8 characters and each one can be one of the 26 uppercase letters, 26 lowercase letters, or 10 digits, that's 62, I guess. 62 to the 8. Whew, that's a lot. Possible passwords. That's not factorial. I'm just excited. So that's without any restrictions. And then we would have to take away the restrictions. So again, it would be really tricky. You take away all of the ones with satisfying none of those conditions. So take away, well, actually, it's not possible to satisfy none of the conditions because then there wouldn't be any letters, I guess. So take away all of the ones that have no uppercase and no lowercase, which is going to be 10 to the 8. Take away all of the ones that have no lowercase and no numbers, which is going to be 26 to the 8. Take away all of the ones that have no lowercase and no numbers, or whichever the other one, which is 26 to the 8. But we're still not done because we still are including a bunch of them that satisfy 2 but not 3 of the conditions. So then you want to take away the ones where there are oh my gosh, this is a tough question. Exactly one of the conditions does not hold. So there's at least one number and at least one lowercase, but no uppercase. So it would be like a subtraction within a subtraction, I think. It would be annoying. Here, these are the cases that fail 2 conditions, just in case you're wondering where that comes from. To get rid of the cases that fail exactly 1 condition, you would have to, let's examine one of them. Let's imagine the cases that only fail the first condition. So they have no uppercase letters, but they have at least one lowercase letter and at least one number. So no upper, at least one lower, at least one number. That's going to be 26 plus 10, so 36 to the 8 minus 26 to the 8 minus 10 to the 8. So that as a whole is the number that have no uppercase letters, at least one lowercase letter, and at least one number. Because it's like we're basically like reducing it to a smaller problem. Like imagine uppercase letters didn't even exist, and then we're starting from scratch, basically saying if we're only allowed to use lowercase letters and numbers, how many ways are there to satisfy a password that has at least one of each? And that's a problem that we've done kind of before. So this would be one of those cases. And then there would be 2 other cases like this. And I think if you subtracted all of those from 62 to the 8, you would get the correct answer. But that's pretty complicated. So hopefully that answers your question. And you can take it from there. Okay. Another question. Are we required to write out the formulas for the distributions, or can we use the shorthand, for example, x tilde bin NP, and then state it was solved using R? Ooh, I never thought about using R for the midterm. You can use a calculator, you don't need to use R, but I think, so that's a great question. So I'm gonna back that up. So like format for solutions, a couple people asked about that. A good way to sort of like format your solutions and like how to make sure that you're showing enough work. So there's kind of a couple of things. My suggestion for any kind of question involving either a probability or a random variable is to basically, step 1, define your thing. So I'd say let x equals blah, blah, blah. So the number of visits to my website in the next hour. And then the second step is to figure out the distribution. So x is, let's say, Poisson, and with the parameter whatever. So lambda times t equals Poisson, say 10, whatever the number is. So that's kind of step 2. And then step 3 is figuring out what you want. So we want, let's say we were asking for the probability of 2 or more hits to the website in the next hour. So we want x is greater than or equal to 2. And sorry, that's a really weird looking greater than sign. There we go. And then you would want to say that's equal to, would calculate that as 1 minus the probability x equals 0 or x equals 1. And then at that point, I would show maybe like one more line of work. Like I would say, okay, this is going to be 1 minus e to the negative 10, and then minus 10 e to the negative 10. And then give the number, 0 point blah, blah, blah. I don't care what the number is. The advantage with sort of structuring your answer like this is that if you make a mistake anywhere, we can still give you part marks for all of the rest. So like if I was marking this and you, for whatever reason, got the wrong t here, like it was actually a 2-hour period and you thought it was a 1-hour period. So you use t equals 1 instead of t equals 2 or something like that. But if you have defined your variable correctly and figured out the distribution, even if you didn't get the parameter, and said what you want and done the calculation correctly, I can give you like 1.5 out of 2 or like 3 out of 4 or whatever. Whereas if all you do is write x tilde Poisson 10, and so the final answer is 0.xxx, it's hard to know where your mistake was. So writing a solution that's well designed is like insurance. It's like an insurance policy on your mark, because you're sort of providing the backup if it turns out that your answer is actually incorrect. Certainly, if all you write is your final answer and it's wrong, you would get 0. No question about that. If you write the answer and you get it right, very likely you would get full marks, but that's a big risk. So again, writing out a well-designed solution doesn't take long. You don't have to have a ton of work, but something like this would give you insurance in case you've made some mistake in your calculations. So I hope that kind of answers your question. The two people that sort of asked about that. Same idea for like any kind of solution involving an event, right? So I'm going to sort of do another one. We're going to just let A equal the event blah blah blah, and then like we want, there you go, equal blah blah blah, and oops, sorry, that's just supposed to say gotta undo that, and B equals 2 events, and then we know like P of A equals blah, and P of B equals, or like say it was like a conditional probability that you were given, equals blah. And then we want P of A and B. And then because we want, you can use the product rule here. It's like P of A times P of B given A. And then you could just give the final number. Whatever. That's the idea. So same kind of thing. Like if you let us know, if you define your events and you tell us what you were given in terms of what was given in the question, and you tell us what we are looking for in terms of the answer, that's like most of the question. And then like knowing which rule to use is another idea. So you could, even if your final answer was wrong, you might be able to get like a good proportion of the marks if you've outlined your solution clearly. Whereas if all you do is write down like your answer without even defining your events, then it's very difficult to give part marks. So that's sort of like 2 questions in one there, and please let me know if that's kind of enough guidance that you want. And again, you don't have to do it this way, but this sort of framework is really helpful in organizing your own thoughts and organizing your own calculations in terms of defining your variables or your events very specifically, and then finding the information that you're given, and then finding the information that you want. The other thing that I was gonna say, if nobody has any other questions, is just sort of a quick bit of guidance on how to know when to use the different distributions, because I think that's sometimes something that people struggle with, just figuring out which distribution to use in which situation. And Audrey posted a great summary that I normally do in class of like all of the distributions and all of their properties and all of those things. Of course, you can look all of that up, but the key is like how to know when to use each distribution. So if there are no additional questions in the chat right now, I will do that. Let me know if that would be helpful. I can just check Piazza one last time before I do something that nobody asked for. Okay, I'm not seeing any objections, so maybe I'll just So thinking about sort of when to use, oh good, someone said that'd be helpful, great. When to use each distribution. There's all sorts of these different ones that we know, right? We know 6 different distributions. There's the uniform, discrete uniform, AB. There's the hypergeometric, NRN. There is the binomial, NP. There is the negative binomial, RP. Or is it K? I can never remember. Someone let me know if it's R or K. Geometric, P, and Poisson, mu. So there's 6 different distributions, and knowing when to use them is a huge part of it. Like that second step of like, let x equal blah, and the second step is x has this distribution. So all sorts of kind of hints here. Discrete uniform, you're going to use that when you know that the outcomes are equally likely. So something like a die roll or something like that, or you're told that there's an equal distribution or uniform distribution over some fixed numbers. With the hypergeometric, the key with this one is that we have to have a total known number of objects. So the total number of objects has to be known, and they have to be classified. Like the objects have to have a classification as like, you know, R successes and N minus R fails. So often a setup for a hypergeometric question is going to have a lot of numbers in it, because you have to be given capital N, little r, and little n, the number that you're selecting. And usually, like, what's the probability that the number that we get is bigger than or less than or equal to some number x. So you'll have at least 4 numbers probably in the question to be able to set up a hypergeometric situation. So that's kind of just a pragmatic way. He'll be given lots of numbers to have all of those parameters. But the other key is that we're sampling without replacement. And as well, we have to know the number of objects that we're selecting. We have to know the number we're selecting, and we count the number of successes. So there are plenty of situations where we have what looks like it might be a hypergeometric situation. One of the examples in the course notes is the one where you're drawing, I think, like light bulbs, like 40 watt and 80 watt light bulbs or something out of a bin. And you're drawing until you get a certain number of one category of light bulb. That's not hypergeometric. Hypergeometric would be, we draw a fixed number out of the bin and count how many of them are the right type of light bulb. That question in the course notes is kind of like a combination between the hypergeometric and the negative binomial, because we're doing something until we get a fixed number of successes. So actually, if we had to give that distribution a name, that would be the negative hypergeometric. But you don't need to know that. It's just kind of like a combination of those two. So for the hypergeometric distribution, we have to know already how many we're selecting and be counting the number of successes. And that applies to the binomial as well. So the binomial, negative binomial, and geometric all use Bernoulli trials, which have 3 conditions. We need each trial is a success or failure. The trials are independent, and the probability of success doesn't change from trial to trial. So probability of success is constant. So all 3 of those distributions use Bernoulli trials. Another way to tell would be if it's with replacement. Or if you see something like, if it says independence, like that's definitely a good clue that Bernoulli trials are at play. But in this case, even though the setup is the same for all 3 of those distributions, what we're waiting for, what we're asking for, what we know in advance is what tells us which distribution to use. So for the binomial, again, we know the number that we select and count the number of successes. Whereas for the negative binomial and the geometric, we know the number of successes that we want, and we're waiting until we get a certain number of those successes and count how many fails. So for these 2, negative binomial and geometric, we know the number of successes, and then we count number of fails. And the only difference between the geometric and the negative binomial is whether the number of successes we want is 1 or something bigger than 1. Is it K? Again, I think it might be K. It doesn't matter what we call it, but I think it's K. Like just what the course notes uses and what the videos use. So with that one, with the negative binomial and the geometric, some key words or phrases that you can look for to tell you that that's what's going on is the idea of like until, like waiting until we get whatever, or like it takes a certain amount of time to get. Like it takes 10 trials to get 3 successes is different than saying we do 10 trials, what's the probability there are 3 successes? And it's a subtle difference. So you kind of have to think about, are we waiting until we get a certain number of successes and then stopping? Is that what's going on? Or are we just doing a fixed number and seeing how many were successes? If it's the most recent thing I said, then it's binomial. If it's the previous thing, then it's negative binomial or geometric. So the idea of like waiting time or something like wait for, or something like that. There's not just a few, there's not infinitely, but there's lots of different ways it could be phrased, but those are some kind of keywords to look for that might indicate that it's a negative binomial or geometric situation. You know the number of successes you want, that you're aiming for, and you're counting up how many fails occur along the way. And then finally for the Poisson, we kind of already talked about this, but there's 2 ways this comes. This could be approximation to a binomial with a large n and small p, or a Poisson process. And again, the conditions for a Poisson process are basically the continuous analog of the conditions of Bernoulli trials, right? With a Poisson process, we have independence, we have a constant rate, which is like uniformity or homogeneity, and we have individuality. Oops, scroll down a little bit here. There we go. So the independence is, again, similar to the independence. The uniformity is similar to the probability of success being constant. And the individuality, I guess that's a different thing because we're dealing with continuous time here. And so a Poisson process, and again, we're knowing the number of, not the number, sorry, but the amount of time that you're watching. And counting the number of events. And there is a continuous time sort of version of the negative binomial and the geometric, but we'll get to that in chapter 8. So with the Poisson process, again, if we want a Poisson random variable, we're counting up the number of events in a fixed or known amount of time, which is, again, very similar to the binomial, doing a fixed number of trials and counting up the number of successes. All right, hopefully that helps. Again, check out the sheet that Audrey posted as well for some other great clues onto when to use the various distributions. And I do see another question came in. I don't remember the specifics, but there was a Mobius question about 2 guns where one had 7 bullets and 4 blanks, the other had 6 blank and 2 live. If the probability is equal to pick each gun, what is the chance of a fired gun firing all blanks? So that would be a use of the partition rule or the law of total probability. So it's kind of a combination of that from chapter 4, maybe with like a little bit of chapter 5 thrown in terms of like the number, like the binomial number of shots fired. I don't think I can answer the exact question like well enough without seeing it. So maybe pop it on Piazza and I can answer it there. But the idea is, you sort of, a great way to approach that problem is to literally write down, define event A to be that gun number 1 is chosen or whatever. And you know that P of A and P of not A are both 0.5. If it was equal chance to pick each gun. And then you can also tell, given the gun, what would be the probability of firing all blanks. And so you have information about firing all blanks given the type of gun, and you want information about the gun given the number of blanks that were fired. And so what do you use when you need to swap the direction of conditioning? Bayes' rule. Bayes' rule. Anytime you need to switch the direction of conditioning, that's where Bayes' rule comes in. So that hopefully is enough help to get started on figuring out that question. It is almost 2 o'clock, so I do want to wrap up, but maybe I'll just write that down as a parting shot whenever you need to know. Swap the direction of the conditioning. That is when you use Bayes' rule. It's great for that. That's what it's for. How do we access the MassDoc exam bank? Oh, someone posted a link. Yes. You might need to log in, and there's lots of great stuff there. Again, the midterms used to be not just in the middle. You will need to log in, yes. And so if you're not a math student, I'm not sure if you're still able to log in. I hope you are. But if you're not, maybe get a friend to send you some. But there's lots of great ones on there. And the midterms, again, they don't correspond perfectly. So if you look at like test 1, it might not cover exactly the same stuff. So you might want to look at test 2 as well, or maybe even test 3 from some terms. And any question that sort of involves random variables or conditional probability, Bayes' rule, that kind of thing, you can usually spot them. Those would be helpful. If it says anything about expected value or anything about a continuous random variable, just ignore it. You don't need that yet. But there's lots of great material there. And as well, there's examples of past midterms in the course notes and in the sort of second set of course notes that are called solutions. And also I posted a practice for part 1 in addition to the practice for part 2 on Learn. Thanks very much for attending. I hope this was useful. Best of luck on the midterm on Thursday. And I will have my normal stream on Friday. So if you want to come back then, we can talk about how it went. I'll also be talking about League of Legends and the importance of unbiased data in terms of machine learning. So some cool stuff to talk about, and also we can go over the midterm if you are desperate to know. You'll have just handed it in the night before. Have an awesome day, everyone. Thanks, and hope you had a good reading week.